let's see. I lost my notes from last time, but I think that we left off just defining Gauss's law. Is that right? Where we said E, or epsilon naught times V, is equal to our enclosed charge. Is that right? Yeah. Okay. So that is Gauss's law. It looks a lot like Gauss's law that we had for gravity. By the way, guys, I haven't updated the equation sheet, but I'll send you an updated equation sheet out today or tomorrow morning at the latest, okay? With this stuff, Gauss's law, the definition of flux, all those various things, escape speed from the gravity chapter, Newton's universal law of gravitation, the gravitational field, gm over r squared, gravitational potential energy, everything that we covered in that chapter, okay? As well as the equations from this chapter. So here, just like before, phi is equal to our flux, which we've already defined. Epsilon naught, I think I've written this down, is that right? Permeativity is free space. And remember, this permeativity of free space is actually related to our K value. K is equal to 1 over 4 pi epsilon naught. And then Q is our enclosed charge. That is the charge inside the Gaussian surface. And that can either be positive, negative, or zero, as well as your flux can be positive, negative, or zero. So that they affect one another. So imagine that I have these two charges here. I have a plus and a minus charge. I can draw my field lines. They look like this. And then if I imagine some surfaces, various surfaces, let's say that I have a surface over here. I'll call this surface 1. I can imagine a surface here. I'll call this surface 2. And I can imagine a surface here. I'll call this surface 3. Now, first of all, I want to ask myself the question, what is the net flux through each of these surfaces? So, for example, is the net flux here positive, negative, or zero? That is more flux going out? That would be positive. Is more flux going in? That would be negative. Or is the same amount of flux going out or in? That would be zero. This has a positive flux. And you can tell, too, since it has a positive flux, then you can also tell that if T is positive, that means Q is positive. All right, so just by measuring the field around this, I can tell whether the charge inside of it is either positive or negative. Similarly over here, positive or negative flux. That is more going in or out? More going in. More. That's a negative flux, right. So flux is going into it, so it's a negative flux. And so the charge inside of it is negative. And how about here? I have some field lines coming in and some going out. What is the net flux here? Zero, right. So the net flux here is zero. So the charge inside of that surface is zero. So here I have a positive flux, positive charge enclosed. Here I have flux equals to zero, and so the charge enclosed is also equal to zero. And here I have a negative flux, and so I also have a negative enclosed charge. So this can be really useful if you're trying to figure out what is the charge within a certain region, because you just measure the fields around it and calculate the flux, and then you can find the charge enclosed. If you have a homework problem, if we have time, we'll look at it, but the solutions are online. By the way, I posted them yesterday or the day before? Yesterday, I think. Yes. They're on the homework site. So look at those homeworks. Your test questions will be similar to them. And we've worked several that are like them as well. So is that clear? We'll go over that in just a bit. All right. We'll just do a quick little example. Simple Gauss's law. Let's say that I have several charges, Q1, 2, 3, 4, and 5. So this will be Q1, this is Q2, this is Q3. These are just sort of charges, they're like little blobs of charge. Q4 and Q5. Alright, and then I imagine a surface. My Gaussian surface here goes around like this. So this is my Gaussian surface. Doesn't really matter what the shape is, I've just sort of drawn it, sketched it in. And I want to know what is the net flux going into that surface. For the surface. Now if I knew the electric field and I knew what the shape was like, then I could do this whole thing with the flux is the surface integral of E dot dA. And we've done problems like that before where I give you a surface and the electric field. But we don't know the electric field, and this surface is just sort of something I made up. So we don't really have a good way to define the area. But I do know these charges. And so the charges are Q1 is equal to Q4 is equal to plus 3.1 nanocoulombs. Q2 equals Q5 equals minus 5.9 nanocoulombs. And then Q3 is minus 3.1 nanocoulombs. So if I know the charges, then it becomes really simple for me to find the flux. Correct? Alright, so here I have 5 charges, but which of them do I consider to find the flux through the Gaussian surface S? I just consider 1, 2, and 3. And so I say, goodness, you okay? Yeah. Alright, so I just say that phi is equal to my enclosed charge divided by that permeativity of free space. So really simple. I just say Q1 plus Q2 plus Q3 divided by epsilon naught. And here I need to make sure I keep the signs because some of these are going to have field lines coming in and some of them will have field lines going out. And so if I want to know the total field lines going through the surface, I have to include the signs of the charges here. So Q1 is a positive charge, Q2 and Q3 are both negative charges. So you can probably look at this and tell, is the flux going to be positive or negative? That is there going to be more flux going out? That is it positive? Or is there more flux coming in? Is it negative? Which do you think it is? More coming in. So the net field lines are going to be coming in because I have more of a negative charge inside there. So Q1 is positive 3.1 nanocoulombs. Minus 5.9 minus 3.1 nanocoulombs. And these cancel because they're equal and opposite, divided by 8.85 times 10 to the minus 12. Alright, and I would do that, I get a net flux of negative 670 Newton meter squared per coulomb. Alright. Okay, so that's pretty simple, but you could see a simple Gauss's law problem like that. I'll provide you with the equation for Gauss's law, and then it's really just a matter of adding up the charges that are inside the surface. And notice here that the charges outside the surface don't have any bearing on it, that it's really just the charges inside the surface that govern what are the field lines. Because while these charges might have field lines between them, if I imagine these charges, let's see, Q4 and Q5, yeah, so they might have field lines that are going in between these charges here, and they might even intersect with the surface somewhat, but whatever field lines go into the surface will also go out of the surface. So they're not going to contribute to the flux around that surface at all. Okay? Alright, let's finish that problem that we did with the cube before. Remember we had the cube last time, we calculated the flux for some of the surfaces. We had this cube. And we calculated the flux for some of the surfaces. I don't have my notes up for that, but we found the right, left, and top faces. and the flux for the right was 36. The flux for the left was equal to minus 12, and the flux for the top was 16. Remember, we did this thing where we had to do the surface integral of the electric field dotted with the area vector, E dot dA. And now the question is, I want to know what is the total charge enclosed inside of this box. The electric field for that was 3xi plus 4j. And I just want to know what is the total charge enclosed inside this box. So I know nothing about the inside of the box. All I know about is just the electric field that this box generates. And so I can calculate now the rest of the fluxes. So there are, what, 6 faces to a cube? So I just need to find the rest of those fluxes and then add them all up. And then I can use Gauss's law to find that total charge. All right, so I have, let's see, I need to find the bottom face. And so the flux will equal to the integral of E dot dA. What is the direction of dA on the bottom face? It's down, so it's negative what? Ij or k? No. J, right. So our dA vector here is going to be dA in the j direction, negative dA in the j direction. All right, so I do the surface integral of 3xi plus 4j. Dotted with negative dAj. And then these are the only two, so I get a flux of 4, negative 4, integral dA. The area of this cube, let's see, the cube was a 2 by 2? Yeah, it was a 2 by 2 meter. Alright, so it's 4 times 4, which is negative 16 Newton meter squared per coulomb. Alright, so that's the bottom face. And then what about the front and the back faces? What is the, for the front and the back faces, what are the directions of the area vectors? So for this face right here, I have an area vector coming out, and then the back face on the back side. Front is positive k, back is negative k. And so if I take a dot product of dAk, whether it be positive or negative, with this electric field vector, what am I left with? It's 0, right? Because there is no k vector in this dot product. So those two faces contribute nothing to the flux. There's 0 flux for both of those faces. Remember, with dot product, I dot I equals 1, j dot j equals 1, and k dot k equals 1. But I dot k, I dot j, j dot k, all those are not, or they're all equal to 0. So our back face and our front face give me a flux equal to 0. All right, because I dot k and j dot k are both equal to 0. Anytime you have two vectors that are perpendicular, their dot product is 0. So we can add up our total flux. Let's see, we have 36, 12, 16, negative 16. That's it, right? And then 0 and 0. So we just say 36 minus 12 plus 16 minus 16 plus 0 plus 0, and that's equal to, let's cancel, right, positive 24 Newton meter squared per coulomb. All right, once we do that, it's pretty simple to find the charge. We just say the Q enclosed is equal to epsilon naught times that total flux and then that's it. Alright, so really the hard part's finding the flux. You'll have a problem like this. It'll be something similar. It'll probably even be a cube, so make sure that you're up on this. Okay, Gary?
Will it include K?
Will it include K? What do you mean? Oh, probably not. It would probably, well, it could include K, but it's probably not going to be a three-dimensional electric field. It'll probably be a two-dimensional. So it could be an I plus K field or a J plus K field. Right. So two of the bases then will not have an electric
So
field.
don't be asking us to find the pieces better than
Well, for example, here, if your electric field was instead, say, 3I plus 4K, then it wouldn't be the back and front that would be 0. It would be the, what would it be? The top and bottom would be 0. Yeah. Is that clear? Uh-huh. Right. We're going to come back to Gauss's law at the end of the semester when we get in. We'll do Maxwell's equations and we'll see Gauss's law again. So we'll probably do a slightly more complicated one. All right? What's that? Which one?
The -4 on the same.
This one?
Yes, sir.
Okay, on that cube, it was a 2 by 2 by 2 cube, and so the area of the face, when we do the integral of this area, it just gives us the area of the face. The integral of dA is just A, and it had an area of 4 meters squared. Right. Okay.
Yes, that's just doing the dot product inside the angle first, -4 on the
Right. That's right. That's right. You just do the dot product, and then you integrate the area. And it's not really integral, we're just taking the area, because it's a really simple shape. All right? Alrighty? Alright. One more thing in this chapter. And I don't know if this was in the notes that I had scanned and sent out to y'all. It's a derivation. It's a simple derivation, but it's a pretty important one. So I could ask you this on the test, actually, to just derive Coulomb's law. So with Gauss's law, you can derive Coulomb's law for a point charge. So imagine that we have a point charge, a positive point charge here, and I want to know what is the electric field around this point charge. So since it's a point charge and those electric field lines go out isotropically in all directions, I can define my Gaussian surface as a sphere. So this is my Gaussian surface. I know that at every point along that Gaussian surface, I have an electric field that's in that direction. And what is the direction of my area vector? Right, it's going to be perpendicular to the surface, which is in the same direction as the electric field vector. So that's my electric field and my area vector. I can say that the integral of E dot dA is equal to Q enclosed over epsilon naught. This is just, flux equals Q over epsilon naught. That's just Gauss's law. I can say then this is the E comes out, it doesn't change. dA, I'm left with that, is equal to Q enclosed over epsilon naught. dA of a sphere, what is the area of a sphere? Which is my Gaussian surface. Remember? That's 4 pi r squared. You're thinking volume of a sphere, which is 4/3 pi r cubed. But the area of a sphere is 4 pi r squared. Don't worry about that. I'll show you. You can remember it just a bit. Equals Q enclosed divided by that epsilon naught. And then, so my expression for the electric field then is going to be 1 over 4 pi epsilon naught Q over r squared. Alright, so that is my electric field. Oh, and don't forget that this right here is just equal to K. If that's not on your equation sheet, it will be that K is equal to this 1 over 4 pi epsilon naught. Alright, so that's Gauss's law we can use to find Coulomb's law. And this is for the electric field, but it's also applied to the electrical force. Because we define the electric field on the electric force, by the electric force. So Gauss's law has a lot of nice applications for determining things about charges and gravity as well. Again, we'll see it again later when we get into light and radiation. All right, we go over the test. What to expect for the test? All right, so we'll see a 2D vector problem. Can I go down from here, y'all? So you will see a 2D vector problem. It could be any variety of things. You had several examples like this in your homework. So, for example, it could be either gravity forces. It could be electric forces. Or it could be electric fields. They all work out the same way. The only difference, of course, is finding the magnitude of the forces. So for the gravitational forces, if I have, 3 masses all together, I would find the magnitude by Newton's universal law of gravitation, that's gmm over r squared. The electric forces, I would use the Coulomb's law, and electric fields, I use that kq over r squared. You'll have some questions about the shell theorem. So you just need to know what it is. You can see this either in the multiple choice or as sort of maybe a 3 or 4 point question and a free response. Answer this in a sentence or whatever. What is the shell theorem? So make sure you know what the shell theorem is. Let's see. We did gravitation near Earth's surface. All right, so find the acceleration due to gravity near the Earth's surface. You had a homework problem about that, finding the acceleration due to gravity at a certain height above the Earth. Gravitational potential energy. How did we do with that? Let me look at the homework right quick. So you had a homework problem like this, number 7, where you find the gravitational potential energy of a collection of mass particles. And we had this homework where you had 3 mass particles, and you had to find the gravitational potential energy. In order to do that, you consider the 3 separate pairs of particles, like this, and calculate the potential energy due to each. We have an expression for that. That'll be on your equation sheet, that gmn over r. And then you add up these 3 pairs of the gravitational energy. And you should look closely at the homework, okay? That's going to give you a good idea of what you should be doing on the exam. And then also, finally, we did, we didn't do Kepler's laws at all. You could see an escape speed problem. We did do that, right? Yeah, I skipped over several things in this chapter. I sent out my whole notes, but you should go back and look at your own notes to make sure that you got what we skipped. But we didn't skip escape speed. It could be a simple problem. I'll give you the equation for it. You don't have to derive it or anything, but just be able to calculate the escape speed. And then Gauss's law for gravity. You'll need to apply that. We did a very simple thing for Gauss's law for gravity, where we just expressed it as g times the area of your surface is equal to our negative 4 pi g times the mass inside. Notice this looks a lot like our Gauss's law for electric fields as well. Except here we had, instead of the gravitational field, we had the electric field. Here we wrote this a little differently, said it was the integral of dA, but it's still the same. And here we had epsilon naught, and this was charge. This looks basically the same. So we did this for spheres, cylinders, and flat structures. I could ask you something like that to find what is the gravitational field due to this sphere, this cylinder, or this flat structure. And you had a homework problem like that. However, I won't give you the equations for those three. I will give you the equations for the area of a, of a sphere and a cylinder in case you forget. All right, on the equation sheet. Let me make a note of myself with that. And just be able to calculate either the flux, or if I give you the flux, find the mass inside the surface. Or no, I'm sorry, be able to calculate the gravitational field. So being able to calculate this G for a given structure. Pretty simple, right? Like if I have a cylinder, I just say G times the area of my cylinder, that's my, 2 pi r/h, divided by the mass inside, or excuse me, divided by negative 4 pi g, and then that would give me the mass of the cylinder, if you know what G is. There's a homework problem like this, dealing with a flat sheet, so if you look at that, it'll be something similar to that. For electric fields and forces, again, you could see a force problem where you have the electrostatic charges. You should know sort of the basics of how electrostatic charges interact with one another. That is, positive charges repel, or like charges repel, opposite charges attract, that sort of business. We did fields as well, or electric forces, a vector problem regarding to that, and then also electric fields. With the electric fields, as in your homework, you could see a kinematics problem. Very simple kinematics problem. It's like a one-step problem where you have to find, given the electric field, you have to find the force, and then you have to find the acceleration, and then either the velocity or the displacement. Okay with that? There's homework problems like that, at least one in a homework. No derivations for the charge, ring, disk, or dipole, but please do bring that on Monday morning. Yeah, remember what I said? So I want you to do either the dipole or the charge disk, and then bring that on Monday morning and turn it in. I'll send an email about the derivations today. And I'll send you the figure that you can just sort of, I want you to fill it out on the sheet. And then interpreting field lines. I might give you a collection of charges and ask you to draw the field lines for those collection of charges. It won't be terribly complicated, probably just a couple of point charges, but just be prepared to either draw the field lines appropriately or interpret them appropriately. All right, so a couple of rules that have to do with that. Field lines come out of positive charges, go into negative charges. The number of field lines coming out of the charge is proportional to the magnitude of that charge. So a charge with twice the magnitude of another has twice the number of field lines. I think most of you have the lab. I know some of you don't, but you'll get that in lab. If you're not sure about that, you can come see me or go back in your notes and learn about that in class as well. Okay? And then there is this latest business that we've been doing. Yeah, actually, you know what? Your derivations are, I think, in the homework video, so it should be pretty easy, but I also want you to write a few sentence description of how to do the derivations. Y'all read that, right? Did y'all know they're in the homework video? No, not yet. Huh? Oh, yeah, yeah. All right. And then Gauss's law, so you'll have to calculate the flux. It'll probably be a problem similar to that cube-like problem. Once you find the flux, find the charge inside of that. And then just applying Gauss's law. And I could also ask you to define Coulomb's law like we just did. And that's it. Yeah, that's all. You have questions about the exam? It's going to be, 10 to 15 multiple choice. Probably fewer multiple choice. That's probably more like 10. And then, 4 to 7 free response, depending on how difficult they are. I expect some of them to be free. No, I'll give you all that stuff. So I'm going to update the equation sheet today, and I'll send it out to you. I haven't made out the exam just yet. What?
Have you checked the homework?
The escape or the gravitation at a height h?
Yeah.
Yeah, I did, and I found the problem. We can talk about it. The problem's okay, and even the way that you did it is okay. There was just an assumption that you made that was incorrect. And I'll show you that afterwards. All right. What other questions? You feel okay about the test? Yeah, up on the homework. Now, you feel comfortable with the homework? I think you'll be just fine on the test. Okay? So, you feel okay with the homework? Okay. It won't be exactly like the homework, but it'll be very simple. All right. Well, 15 minutes. Huh? Alright, I'll tell you the funniest joke in the world. You want to hear it? And then we'll call it quits. Because I'm taking this class on interpersonal relationships, and one of the chapters was on language, and in the language section they had a section about humor, and they told this story about this guy that set out to find the funniest joke in the world. And he, I bet it sounds like a joke. This isn't a joke. But he put together a website, and he put 40,000 jokes on the website, and he invited people to come in and rate which they thought was the funniest. And then after like a year of doing this, he produced the funniest joke in the world. You want to hear it? Like, this is a scientific study. So there were two guys, and they were out hunting. And something happened to one of the guys, and he like fell down, and he turned white, and he stopped breathing. It was bad. And so the other guy, of course, freaked out. Right? And he had a cell phone, so he called 911, and he told the operator, "Hey, I'm out in the woods, we're hunting, and my friend, I think he's dead." And the operator said, "Sir, please, just calm down. I'm sending help right now. But first, you just need to go check on him and just make sure that he's actually dead." And so the guy said, "Okay." So I went over, and then the operator in the background, he heard a shot. Bang! And then the guy comes back on the phone, and he's like, "Okay, now what do I do?"
I'm not sure if
They
there's
actually
a
made a
commercial
commercial
for a long
like that.
time.
What's that?
They made a commercial like that.
Oh, did they? Okay. Alright guys, well that's all I have. So unless y'all have specific questions, we can do that. Did we go through them? Yeah, we didn't have them for the gravitation, for the distance. I'm sorry. So most of your multiple choice will be on electric fields and forces. Alright? You might see some questions about the shell theorem and stuff like that. Okay? I'm sorry. I didn't have any for this one. Okay guys, well, I'll see you on Monday.